Gently. Shiauchu. Mayorish. Songyang. Lee. Xiaobu New. Ashkan.
Thank you.
Joseph. Muhammad. Ning. Shen. You have all your stuff. Hopefully I'll give you the midterm grades will be posted this week. We're done with quizzes, 4 quizzes so far. The last homework, the 4th homework will be posted today and will be due in 2 weeks. It doesn't need 2 weeks, but just to take your time to work on. It will have maybe 2 problems in calculus operations, you can do them now. 1 problem on today's stuff, you can do it. Then the rest of the probably 2 more problems will be done based on the stuff that we will have next 2 times. So it will be due last Friday. This is 4 homeworks, 4 quizzes. They have, what, 40%, right? The worst of the 2, the worst of these 8 items will be dropped, okay? Then the midterm is 20%, the grade will be posted this week, and then the final 40%. We'll talk about the final later on. So today we're continuing with differential geometry, and this is one of the few lectures that it indeed depends on the stuff from before, from the last lecture. Yes, you?
When do we turn the homework on Friday?
We'll talk about that later. Basically, my office is on particular hour or so. So, we're still with differential geometry, and we're going to need concepts from last time. Last time we introduced differential geometry, and we said that it's basically a language. We had learned several words, right? Maybe 4 words. Let's just revive our memory about these 4 words. We learned, anybody remembers the basic word?
Manifold.
Manifold, very good. And we said that a manifold is just a curvy space, right? But locally, it has to look like, locally here, if you zoom, it has to look like a flat space, and to make sure of that, or to make it formally look like a flat space, we need a map that maps this neighborhood to a flat space. And this map has to be smooth, invertible, its inverse smooth, the best map ever, okay? So this is a manifold. We also defined the second word, which was the curve on a manifold. This is very easy to visualize. If this is your curved space or whatever, then a curve is just a curve passing through a points on the manifold. Again, formally, to us, this is just a map that maps from the real line to points on the manifold. This is our gamma. So gamma is a map from 0 to maybe large T to points on your manifold M. Okay? So gamma of T, the curve on the manifold, has n components on the manifold, right? So, then we said that this is a curve on the manifold, we can define the velocity of the curve on the manifold, just differentiate with respect to time. And then we defined the tangent space, right? 3, the tangent, the third word was the tangent space at a point. So this is your manifold, maybe a sphere. At this point, this is the tangent plane, which we call the tangent space here. At this point, this is the tangent plane. But more generally, the tangent space at the point, it's defined only at the point T, P, M. Tangent space of M at the point P is, as you see here, the tangent plane to this sphere at this point is different from the tangent plane at that point, right? So, the tangent space, if it's a curved space like this in the curved surface, then it's just the tangent plane. More formally, it's the collection of all velocities of curves passing through the point, right? This was the formal definition of the tangent space. And we said, well, it's the collection of all velocities of curves. So at this point, this might be a velocity of a curve, v1, this might be velocity of a curve, v2, it lies in the plane. Any v in the tangent space, we call it a tangent vector, right? It's a velocity vector of some curve. If M, the manifold, is n-dimensional, has n components, n configuration coordinates, or whatever in our language, then the tangent space is also n-dimensional, but it's flat, right? The tangent space is a flat space, not Euclidean, it's a vector space. This guy is a vector space. We get this for free. It's a vector space. What do we mean by a vector space? It means that we can add vectors. We can add elements of it. Of course, its elements are vectors, velocity vectors, right? We can add velocity vectors, subtract, or multiply with a constant. So this is what we mean by a vector space. You can add things, because in general we said, we may not be able to add things. Simply, I cannot add points on the manifold to get a point on the manifold, right? Addition is not even defined. But here, the tangent space, you can add things. And what's the dimension of this space? The tangent space is the same dimension of the manifold. The manifold is curvy, but this guy is a bit flat. It's a vector space. It's the same dimension. The sphere has two dimensions, right? It's the two dimensions. Because you need just two coordinates on the sphere to completely describe a point, right? Longitude and latitude, or whatever, theta and phi. The tangent plane is two dimensions, it's a plane, right? Whereas the circle, for example, this is 3 dimension, this is x, y, z. But if we work on the plane, and this is just a circle, the tangent of the circle at any point is just a line, right? So the circle is 1 dimension, any point completely characterized by 1 coordinate, theta, and its tangent is also a line, 1 dimension, okay? So this is the tangent space idea of the word. But any vector in the tangent space, last time we said, well, if this is the tangent space of M, and M is n dimension, then this V is V1 up to Vn, right? Components of a vector, it's a vector, right? And we write it V1 E1 plus Vn En, but last time we said in differential geometry, our bases are not ijk or E1 up to En. It's differential geometry. Actually, they are differentials. Partial x1, partial xn. So that if this vector acts on a function, takes a function, so takes a function f, so we write it as v of f or vf. This is what? This is just multiply this guy with the function f. So you will get v1 partial f partial your x1 yada yada vn partial f partial xn, or if you just summate 1 to n vj partial f partial xj. Last time we said this is already known to us as nabla f dotted with the v, right, as vectors, which we call the direction derivative. We're going to talk about it again today in more detail. But to us, any vector in the tangent space, we view it as acting on smooth functions. It differentiates the function, gives you a real number, because at the end of the day, we have to substitute here at the point P. Because v, little v, is the tangent vector is defined only at the point P. Okay? So at the end, if you're going to substitute the point, you will get a number. So actually, V in TPM, V takes smooth function on M. This is how we write it. See, infinity, it's infinitely differentiable. You can differentiate it many times. Defined on the manifold, right? So it takes a function and gives you back what? A real number. Okay? This is V. This is what we had been talking about last time. So, did we define something more? I guess that's it. We're going to add to our knowledge today, our knowledge of these words, of differential geometry, the language. So, probably the fourth word, we're going to talk about vector field. Any questions so far? So this is pretty much our lecture last time. We did some examples. Any question? I mean, these things need deep thinking to understand and to absorb. So if you have any question, just please bring it. Yes, Shahuz?
So this is only applied to a space with points, like not a space of like matrices like we saw last time.
Can apply to anything, right? We said as long as it abides by the word manifold.
So when you say evaluate by a point, then you have a field of manifold of matrices. How does that work?
This concept?
Yeah.
Yeah, it takes a function on the manifold. What do you mean by function on the manifold? Your manifold is a set of matrices. So your function by definition takes a matrix and gives you a real number. Any function that operates on the matrix, maybe determinant. The determinant is a function that takes the matrix elements and gives you a real number, right? So then your tangent vector will take the determinant and gives you a real number. What's that? It will be the change of the function along your vector. Just differentiate your function with respect to the entries and do the dot product. This is what does it mean. And we'll talk about this particular thing over here in more detail. And your question about the matrices thing also in more detail. Actually, vector field simply is the generalization of this thing. If tangent vector V is a velocity vector at a point, so it's only defined at a point, in the tangent space of a point. The vector field is defined everywhere on the manifold. So at every point, it gives you a vector in the tangent plane. So at this point, gives you a vector in the tangent plane. At this point, gives you a vector in the tangent plane, a vector in the tangent plane, and so on and so on. Okay? This is vector field. The vector field takes a point P in M and gives you back a vector, right? V that is in TPM. At any point, it gives you a tangent vector to your manifold at that point. Like what? Like the velocity vector. Say we are here in R2. This is not a, it's not a hard thing to imagine. This is, this is your X and Y, you have a velocity field, for example, which means at every point, you have the vector representing the velocity of the air or whatever. At any point, you have the velocity vector. At any point, you have the velocity vector, right? At any point, you have a vector. So maybe here is an example. Vector field large X on R2. So X in general is a function of the point, right? Maybe here it is x, y, x squared plus y squared. That's fine, it has two components, right? It's a vector in two dimensions, it has two components. But the components, they are each component is a function of the space, right? So it's a vector valued function. This is how we think of it. It's a vector valued function, but it's not any vector. This vector has to be tangent to the manifold. This is the point. It cannot be just any vector. It has to be tangent to the manifold. Okay? Any question about that? So this is what we mean by vector field. So In this regard, since at any point it gives you a tangent vector, then x, when it acts on smooth functions, gives you what? Anybody can imagine? If a tangent vector at a point takes a smooth function, returns you a number y because we're substituting at that point. It's only defined at that point. This guy is defined everywhere. So it takes a function and differentiates it. It will return you back what? It will return you back another function. Why? Because simply we are not substituting at the point. Just take an example. Here x of x, f is maybe what? X squared plus y cubed, okay? I have a tangent vector v that is defined at maybe t any point, maybe point 1 and 0, okay? Of the manifolds R2. V is just 1 and 2, okay? This is a tangent vector. What is Vf, or V acting on F? What's that? Well, it's V1 partial f partial x plus V2 partial f partial y, right? V1 is 1. Partial f partial x, just to go and differentiate it, please. Here's my function. So it's 2x plus V2 is 2 times partial f partial y is 3y squared, correct? And I cannot stop here. Why? Because this v is defined only at a point. Here is the point. So I have to substitute at the point. All this guy is at x equals 0 and y equals 1. This gives you 6. So the tangent vector takes a function and gives you a real number. Okay?
Professor, why the point is 0 and 1, not 1 and 0?
Oh, I'm sorry. You're right. Thank you. It's 1 and 0. Whatever. I will make this. It's an example. Thank you. It's the point that is given. Okay? Whereas if I apply now, I have this x. If I apply x to f, well, it's the same thing. x1 partial f partial then the x plus x2 partial f partial y, right? What's x1? x1, first of all, is not a number, it's a function. Partial f partial x is 2x. The exact same thing. Plus x2 is x squared plus y squared times 3y squared. And I'm not substituting at a point. So the result is just a function. It's as if